They blow in from the sky, choking us and blinding us.
I cannot see at all.
They are dust storms, and they can be devastating. But there's still a great deal about them we don't understand. This scientist is determined to reveal their secrets.
It's like being a detective. Where's the evidence? What's happening in the atmosphere that's generating those dust storms?
Unraveling the mysteries of a fearsome force of nature. In the beginning, it looks harmless. Just a patch of swirling soil being lofted into the air.
But if the wind speeds are high enough, and if you have an area filled with a lot of this fine sediment, you can generate for hours and hours lofting of material up into the atmosphere.
That's what gives birth to dust storms. They can stretch for miles, rise thousands of feet, cripple whole cities, damage our eyes, our lungs, and even our hearts. And today, the danger is only growing because of climate change. Rising global temperatures are making soils drier and dust storms more frequent. To make matters worse, we're not very good at predicting when they will strike. In the California desert, about 100 miles east of San Diego,
I brought a crowbar. I guess you can try to
atmospheric scientist Amato Evan is directing a project that's taking on this global threat. He's trying to extend the reach of our most valuable storm predicting tool.
Here's an updated look at the forecast.
No, it's not our local TV meteorologist. It's actually something called a mathematical model. It uses sets of equations to represent the complex interplay of forces in nature. A weather model crunches so much data, it has to be run on a supercomputer. The model predicts how variations in temperature, wind, or humidity will interact to cause rain, snow, tornadoes, or hurricanes. Today's forecasts of those storms are very reliable because of those mathematical models, which are based on decades of research into the physical forces that create those kinds of storms.
They bring that Saharan dust all the way across the Atlantic.
But when it comes to dust storms, our knowledge of those forces is sketchier.
You have to have some kind of model in order to make a prediction about what's going to happen. And the predictions that come from that model are only as good as the physics that that model can represent. So if we have an overly simplified understanding of the physics of dust storms, and if we built a model that's not very good, then the predictions that come out of it are also not going to be very good.
It's like here.
To improve scientists' understanding of dust storm physics, Amato and his colleagues from the University of California at San Diego set up a research station here.
Oh, okay. I'll follow you.
They've installed instruments that are constantly recording data about dust storms. They happen frequently out here, which is why Amato chose this desert region for his multi-year study. Even though one senior colleague told him he'd be wasting his time.
I suppose one reason that I got drawn into science is you can be a rebel and be a scientist, and in fact, in some ways, that's really great. When I was younger, I used to skateboard, I hated authority, I used to get in trouble from time to time for going into someone's abandoned house so we could ride our skateboards in their empty swimming pool. And that kind of attitude, it actually translates into science pretty well, because that ability to reject authority or reject what is commonly accepted is what leads to some of the most interesting discoveries.
Amato thinks that his work could advance our understanding of dust storms, no matter where they take place.
This is a natural laboratory for what's happening in all these other places where we can't get to. We can't, go out into the middle of the Sahara Desert and make these types of measurements. It's just logistically impossible to do. Basically, get above these clouds where the weather's kind of interesting.
Most of the dust that forms storms in this region comes from the desert floor. But there's a second and possibly more harmful source: soil that until recently lay at the bottom of this big lake. Known as the Salton Sea, it's been shrinking for decades. In part because much of the water that feeds it has been diverted for drinking. But also because of climate change. As desert temperatures keep increasing, more and more of the sea simply evaporates. And the Salton Sea is far from unique. The same combination of forces, water diversion and climate change, have dried out other big lakes around the world, such as Lake Ormia in Iran, Lake Tuz in Turkey, and the Aral Sea in Central Asia.
All of these types of regions are getting drier as the planet is warming up. So now, when there are large windstorms coming through the area, they just lift up massive amounts of dust.
In California, the increasing volume of dust blowing into Salton Sea communities is making more and more people sick. A recent study found that the rate of childhood asthma here was more than double the national average. And toxic chemicals from nearby farms have seeped into the sea, making the dust from its dried lake bed even more damaging to people's health. Amato's research could help people to reduce the risks they face by improving the mathematical models for dust storm prediction. The key to doing that is gathering lots of data. It starts with measuring how much dust is in the air and how it moves over time. To do that, Amato uses a laser scanning device called a ceilometer.
So we have a laser, and it's constantly shooting light into the atmosphere. And that light hits dust particles, and then that light's reflected back to the instrument, and we make measurements. And that tells us a lot of information about where dust is in the atmosphere and how frequently there's dust. Is it dusty more in the afternoon, or is it dusty more in the morning?
Amato is also collecting data about the second key ingredient in a dust storm: wind.
Dust storms can only be created if you have high wind speeds. And high wind speeds are brought down to the surface from somewhere else, from higher up. But if you want to understand what's generating those dust storms, you have to understand what's generating those high wind speeds. Do you want to get that radio sound going? And really, the best way to do that is something that seems like a really old technology, but it's just attaching an instrument called a radio sonde to a balloon and letting that balloon fly up through the air.
1, 2, 3.
The radio sonde collects data about temperature, humidity, and wind speed, and transmits it to the team's computer on the ground. Back in his lab in San Diego, Amato and graduate student Alexandra Kawano pore through the data they've collected.
Right here at 5 o'clock, of course, that's when the dust starts arriving. And I think the most dust passed over the site around 8 o'clock. Right? Boom.
They're looking for clues that can lead them to a richer understanding of these mysterious storms and better mathematical models for predicting them.
Right after those high clouds go away, like boom, that's when the dust starts kicking off, right? So we have these high. I'm hoping that doing this work eventually is going to help the scientific community make better predictions of what's going to happen with dust in the future.
Send it out a little more, you think it's good?
That's incredibly satisfying to know that we're really advancing the field, that these measurements that we're making are likely to be really useful for a lot of other people. And that's a great feeling.